Hello everyone and welcome to this lecture. In the last lecture we have seen that for a connected non-bipartite graph where you can allow the positive weights on edges, the random walk always converges. It converges to something called stationary probability distribution. Is nothing but the ith entry of that vector, of that distribution vector, is nothing but the weighted degree of the ith vertex. Okay, and of course we are dividing because we are normalizing this vector, so we have to divide each entry with the norm of that vector. Okay, so basically in terms of weighted degree of the any vertex, we can actually tell what will be the stationary probability of being at that particular vector, okay, after sufficient long time. And how we reached to this conclusion? We reached to this conclusion by making beautiful use of eigenvalues of W tilde matrix, right? W tilde matrix is nothing but, if you recall, it's a matrix corresponding to generalized lazy random walk. So let me have a quick recap of previous lecture, and then we will see that. And then after recapping the previous lecture, today we are moving for an exciting journey. The journey is determining how fast we can achieve to the stationary probability distribution, in how many steps we can achieve, right? And we will see that again there is a very beautiful use of eigenvalues of W tilde. Okay, very good. So let me revise slightly. So we see that your PT was given by this quantity. So let me first write it, and then I will copy this part, and then I will move ahead with this exciting result. So basically recap. Let me write recap here. So recap. Okay. So basically your probability stationary probability distribution was given by this, right? Your degree vector, and then you are actually summing over divided by because you are making normalized. So this is degree of i's, yes, and then I equal to 1 to n. Hopefully I am writing it correctly. And then there was one more term which was actually diminishing very fast if when t goes to bigger. So this is done, and then d half times, very good. So plus d half times I equal to greater or equal to 2, then wi, this is ith eigenvalue of W tilde. So let me first write to the power t, and then ci xi. Let me check whether I have written it correctly or not. Yes, very good. So and this is the eigenvalue. Wi is the ith eigenvalue of omega tilde. Okay, very good. And we have proven that these lies in between 1 and -1, right? Okay, very good. In fact, W2, this is not omega, sorry, this is W. If I call it omega, so it's a W2 is always lesser than W1 because the graph is connected, right? We have established this yesterday. Okay, very good. Now we will see that that exciting part is we want to now establish how fast your random probability this stationary probability distribution is actually converging to basically any you start with some at some vector. Okay, so now our next target is what? We want to know random walk how fast is achieving its stationary distribution, stationary probability distribution, and this part we call pi, right? This is a stationary distribution. Our next exciting target is this. Suppose you are starting at vertex u. Okay, now you know that after some time probability at being at some vertex become constant, but now question is, what is that sometime, what is the rate of achieving that probability? Okay, so let me first write down the theorem. Okay, so what will be the rate to achieve that probability, right? And then let me write this, and then we will prove this beautiful phenomena or beautiful result. Okay, so theorem, suppose the random walk starts at u. Okay, and for this result purpose I will assume that, because we are considering a case generalized lazy random walk. So suppose your alpha is always greater than half but less than 1. In that case, then for and let alpha is greater, then let me write the beautiful result, and then we will prove that. So the probability, the stationary probability at v, okay, after some time, because probability is become constant. So suppose the probability of being at v at after some time, how far it is from its stationary probability. Okay, this is always less or equal to the degree of v divided by degree of, so these are weighted degree, and then w2 to the power t. w2 is the second largest eigenvalue of bigger w tilde. How to prove? So you see that means if w2 is small, right, this the left hand side will be smaller, right? In that case your random walk achieve the stationary probabilities very quickly, right? Okay, so let us try to prove it. So I am not proving for whole vector, it is just for one entry, but it's a similar for it. Just instead of dv you replace by dv of that corresponding vertex. Okay, very good. Proof. Okay, now yeah, so I need some notation. Okay, so first notation is, maybe just one notation I will be requiring. Okay, by delta v I mean a vector is a vector where the vth entry is 1 and the rest of the entries are 0. The rest of the entries are 0. Very good. Now you see that what will be PTV from this equation, right? What will be PTV? So if we see that PTV is nothing but, I will take transpose with PT, right? This will give the vth entry of PT, which is nothing but actually, because the PT is stationary probability vector plus this vector, right? So let me first write that this will be nothing but the vth entry of stationary distribution plus I have to multiply with this, right? So it is delta v times d half summation over I equal to 2, and then wi to the power t ci xi. Very good. Shortly we will see what ci will be. Okay, so now if you okay, let us see what ci is. Okay, let us see what ci is, right? Ci is nothing but, if you multiply the xi vector with, remember in the last in the last lecture actually we have indeed calculated Ci, right? Ci was given by, let me show you that expression, then it will be easily follow. Yes, so maybe somewhere here, no, okay, so let me, yeah, so Ci was this, yeah, so Ci, you can see that you can multiply the ith vector, so xi transpose this quantity. Now remember, but P0 is the initial probability distribution, right, we have taken. But here what is the initial probability distribution? It is nothing but delta u, because we are starting at uth vertex. In that case it will be at u position there will be 1 because we are starting at this, and rest of the place it will be 0. So instead of P0 I will be using delta u, right, and then I will take xi transpose of this, right. So let me write this is, now this is very straightforward. So d to the power, I hope this is d minus half, I hope this is d minus half, yes, this d minus half times, very good, so d minus half times delta u, okay. So this is your basically what we call Ci, okay, this is your Ci, and like we have done it here, so we can find Ci. So here I have calculated actually C1 somewhere, maybe below, okay, so anyway let me calculate it again, okay. So what will be this quantity? So what will be this quantity? So if you expand it, okay, so now this quantity, if you see it carefully, so you are indeed dividing for this vector, right? So delta u vector at uth position you are dividing by what? The square root of degree of ith vertex, weighted degree of it. So this will be nothing but xi transpose, and then you are dividing, so basically this will be nothing but delta u, and where the ith portion is actually you are dividing by the square root of du, okay, due to this, right, very good. Now let me plug this quantity into this, right, okay. So let me write this quantity here, right. So this will be what? So let me write delta v t d half, okay, summation over I greater or equal to 2, and then omega I, I am again calling it omega, this is wi, sorry, wi to the power t, and because Ci is constant, so I can take actually outside, so I can write it here xi times this xi to the power transpose, and then delta u, and in fact I can take this square root of d outside, right. So let me first write here itself, which will be further equal to, now similarly I can write this quantity also. What will be this? You are dividing that the vth entry by the degree or square root of degree, right. No, you are not dividing here, you are in fact multiplying here, right, you are multiplying here. So this will be nothing but, so delta v, right, and then times, in fact this is equal to, so let me write earlier also, so this is degree of v, now let me take this outside, so this will be degree of u. Now things are pretty much easy here, I equal to greater or equal to 2 wi to the power t xi, then xi transpose this, very good. What next? What next? Can I take my w, this v inside, and of course I can take it, of course I can take it because this is eigenvalue, so I can safely take it. So maybe I can write this as dv du, and then what? This is omega I to the power t, then you are taking this vector inside, and transpose xi transpose delta u, very good, up to here it is clear. Now what? Let me solve this part separately, Okay, so this guy will be what? So this guy is nothing but summation over here. So I equal to greater or equal to 2. This guy is nothing but w I to the power t. Then let me copy it. Okay, very good, and I greater or equal to 2, right? Now since we have taken alpha to be less greater or equal to half and less than 1, so it's easy to check that alpha i's are actually between 0 and 1, and so I is actually so between 0 and, so it is actually less or equal to, so you see that these are equal to 0 or 1, right? Now what? Now what I can write, you see that because wi's are positive number, right? So then this will become, yeah, this quantity is always I can write it as this, right? T, and then I can take mod here, right? Xi, very simple, right? Very good, up to this is clear, greater or equal to this. Now in fact, since out of all these wi's, w2 is the largest one, right? So maybe I can take this outside, maybe I can take this quantity outside. This is further less or equal to, this is further oh sorry, this will be summation. Yeah, I am making some mistake here, so let me write it clearly here. So this is less or equal to summation over I greater or equal to 2, right? And then this further is less or equal to omega w2 to the power, and then I greater or equal to 2, and then what? Yeah, same thing, right? Let us be very careful here. Xi, then very good. Okay, now in fact these are positive terms, so I can actually add one more term here to make it look more what should say easier. So basically I can now express greater or equal to 1, and then I am adding this because these are positive numbers, so now I can safely write this, right? So Xi transpose, very good. Okay, now what is the next thing? What is the next thing that I can, basically I have to prove that, what I have to prove, can I prove that this quantity in fact yeah, so if I can take here this quantity is always always greater or equal to yeah, but how to, right? Can I make, so what is, by the way, these vectors, if you see here, so by the way, what are these vectors? So if you see that these i's are what? These are eigenvectors corresponding to A, right? So and this tells what? This for all I equal to 1. So basically, so let me first write it here in the, this is rough work, then it will be clear, right? Rough work is this. So x1 vector, x2 vector, and so on, xn vector, right? And that this quantity does what? So this means is this, basically the vth entry of this, vth entry of this, vth entry of this. So this will be again a vector, right? And you are taking mod of this, right? You are taking ideally the mod of this, right? And similarly, this is the uth entry. Similarly here, so somewhere this is v, similar, and suppose there is somewhere here u, right? So uth entry, this is also a vector, and this is basically, if you take all this is nothing but sum of this plus sum of this, right? This mod u. Now using very good, using Cauchy interlace, so not Cauchy-Schwarz inequality, you can actually write this in, this quantity will be always lesser than basically the, I would say, norm of this, right? Norm. Right now what is, we are adding just there mods, but this is always lesser than square root of this square plus this square plus this square due to Cauchy-Schwarz. So I can write now this as, for the less or equal due to Cauchy-Schwarz inequality, as this. I can take this sum inside, the summation over I equal to 1 to n, right? I mean, I'm not writing it, so it will be n to n, and then this quantity square of this, right? And then similarly you can actually write, yeah, due to this I equal to 1 delta u then xi. Very good, these are square terms, right? Square term. Now what is this quantity? Can you check what will be these quantities? What will be these quantities? If you see that these are nothing but norm of this, right? Norm of this vector and norm of this. Basically you are squaring the each entries and then adding and then taking square root. But these vectors are, if you take, so these vectors are what? Normalized vector, right? These are, in fact, so this, if you take this matrix, as suppose this is bigger matrix, x transpose x is equal to I equal to x transpose x into x. So that means this vector must be also normalized 1. So this has to be equal to 1. This must also be equal to 1. Hence this is equal to, in fact, W2 times this. Very, very good. So let me finally come to the conclusion. So what I have to prove is, now I think I have deduced this quantity. So now, in fact, yeah, so you can take actually mod here also. There is no issue. You can take the mod here. So this quantity will be always greater than this because omega is positive. So now what? So you can indeed write again the same thing. Pt V minus omega V, right, is always less or equal to, we have taken this ratio, right? We have this ratio was somewhere this one, and then this quantity is always lesser than. So basically is always lesser than this ratio times. So dV times divided by du and W2 T. Very, very elegant result. Okay, what does this say? This says that smaller this lambda 2, faster will be the rate of convergence. Faster will that stationary probabilities will be achieved. Okay, very good. So, and okay, and now I have not told you about what will happen when this alpha is less than half. This we can, you keep on thinking on that, what will be the case in that case, and we will see in the tutorial most likely, or assignments. Okay, so I hope you enjoyed this. There were slightly, small details were there. So, more calculations were there, but I hope we finally reached a very beautiful result. Okay, so with this I am achieving, I am stopping this lecture. So see you in the next lecture. Thank you very much.